Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's Scribblecast of organic chemistry lectures and solutions to homeless problems. In this Scribblecast lecture, we are looking at benzene and aromaticity. This is the first Scribblecast lecture I'm recording in our new renovated offices, and I'm actually recording them on a new Apple laptop computer. So hopefully this will turn out adequate. Benzene is one of the simplest aromatic compounds, first isolated in 1825 by Michael Faraday. Before the 1940s, the principal source was coal tar. Today it's petroleum. From these sources, aromatic hydrocarbons such as phenols and heterocycles are obtained. Aromatics are important in biological systems, being found in amino acids such as phenylalanine and tyrosine and steroids. Now, the nomenclature of aromatics we have basically covered, and we're going to review most of that nomenclature here, including providing specialized names. Remember, in many cases, the common name has been adopted by IUPAC. For example, if I have a molecule like this, the IUPAC name for this molecule was determined by naming the ring, benzene, and in cyclic molecules you add the ending carboxylic acid. So this is benzene carboxylic acid. Oops, forgot the X. So benzene carboxylic acid. Benzene carboxylic acid. Now the common name for this molecule was benzoic acid. You'll notice, however, that when we actually name this molecule, we always call it benzoic acid. This is an instance where the common name has been adopted by IUPAC and should be noted as the only name. The name benzene carboxylic acid, although legitimate, is hardly ever used. Let's look at some other names, common names, that supplant or often used in preference to the IUPAC name. For example, the name methylbenzene is also hardly ever used. In place of methylbenzene, we use the common name toluene. Toluene is a common name that's been adopted by IUPAC. If you have two methyl groups off, these are called xylene. Dimethylbenzenes are referred to as xylene. Now, xylene can come in one of three forms. It can come, and we're going to talk more about this nomenclature for disubstituted. If we substitute when putting the arrow, that's an ortho form. Ortho is often given the prefix O. If it's substituted here, that's called meta. It's often given the prefix M. And if we substitute here, where I'm going to put my substituent, this is para. Para is often given the prefix P. So the common name paraxylene is often acceptable. You can also refer to it as 1,4-xylene or 1,4-dimethylbenzene. But xylene is often used in place of the term dimethylbenzene. Okay, some other structures. An aromatic ring that has a vinyl group is not called vinyl benzene, but has a special name. And that is styrene. Aminobenzene has a name we should be familiar with. NH2. Has the common name Aniline, which is adopted by IUPAC. If we place an H on aniline and add a C double bond O, the CH3, an acetyl group, this is called acetanilide. Acetanilide. If we continue with this, a common name for a molecule of hydroxybenzene that is adopted by IUPAC is the molecule phenol. If the H is replaced by a methyl group to give you methylphenyl ether, that has the special name Anisole. This molecule, which we covered in the alcohol section of the course, a useful reagent for making inorganic esters, sulfonates, has the IUPAC name para-toluene sulfonyl chloride. Para-toluene sulfonyl chloride has a common name Tosyl Chloride. So if I ask for common, give me Tosyl Chloride. If I ask for IUPAC, give me para-toluene sulfonyl chloride. If I say acceptable, you can call it either. And we have some ketones with aromatic rings on them. Methylphenyl ketone is referred to as Acetophenone. Acetophenone. If we add a couple aromatic rings, not just one, Two aromatic rings on a ketone, diphenylketone, is called benzophenone. Benzophenone. Now, as I said, some common nomenclature is used more often than others. In this course, if we have two carboxylic acids off a ring, I expect you to use the IUPAC name when I ask for IUPAC, and common if I ask for common. If I say acceptable name, you can use either. So the IUPAC name for this molecule, of course, is benzene. One, two, dicarboxylic acid. The common name is phthalic. And there are several versions of phthalic acids. We'll discuss these in a while. If we have a benzoic acid, ortho to a hydroxy group, that is a hydroxy benzoic acid, you can use as both IUPAC and common the term salicylic acid. Note, salicylic is the precursor to acetosalicylic acid, or aspirin. Now, in terms of dye substitution, you often have, as I stated, the possibilities of ortho, meta, and para in the name. For example, take this molecule. One can think of several possible names for this. For example, one might begin by saying this is 4-amino 1-hydroxy benzene. Well, the problem with this name is that there's no priority group in the root. And it violates our IUPAC rules that states that the priority functional group should be incorporated in the root name. So another name you may come up with is saying hydroxy, okay, 4-hydroxy aniline. In this case, the molecule is correctly named in that you are giving the aniline root priority and therefore counting the NH2 as 1. If you use the name aniline, you've got to use number 1 for NH2. That makes the hydroxy 4. Note, you could have also said para-hydroxy or p-hydroxyaniline. However, if you check your prioritization rules in nomenclature, you'll find that NH2 is lower priority than the hydroxy. So there is still a better name. And that would be 4-aminophenol. 4-aminophenol is actually the best name because hydroxy groups are higher priority than NH2 groups in regular nomenclature. Hence, 4-aminophenol we would use as the IUPAC name. Para-aminophenol will be the common name. But I admit that you can use para, ortho, and meta in IUPAC nomenclature as well. Okay, let's try another one. Well, we could go through the same listing that we went up there. We could call this, 1-amino 4-methyl benzene. But obviously that's not the correct name, so I'm going to forego that. This is an interesting molecule because it gives you several possibilities. For example, you could call this molecule 4-amino toluene is one possibility that jumps to mind. The problem with this name, of course, is that methyl is not as high priority as NH2, so toluene is not the best route. Notice you have to call it 4-amino because if you use the word toluene, you're giving methyl priority. And if you're going to use the name toluene, you must number the methyl as 1. And so 4-amino toluene would be correct if methyls were highest priority. But it's not. And hence, 4-methyl aniline is a superior name because NH2 is higher priority. However, there are cases where there are molecules out there that have common names that have been accepted by IUPAC, and this is one such molecule. Okay, and this is 1,4-toluidine or para-toluidine. Para-toluidine is the best name to use for this molecule. So sometimes you find nomenclature that is acceptable for these molecules that have specialized names. Now what happens if we start going to more substituents than 2? Well, the first thing to note is you can no longer use ortho, meta, and para. Ortho, meta, and para is restricted to only 2 substituents. If you have a molecule that has more than 2 substituents, you must number it. Note the highest priority group gets the lowest number. So, the lowest number goes to the highest priority group. In this molecule, highest priority group is carboxylic acid. The root name becomes benzoic acid, and as soon as you say benzoic acid, you have to number from the CO2H. Of course, there's 2 directions to go. We could go 1, 2, 3, 4, 5, which would give me a 2, 3, 5. Or we could go 1, 2, 3, 4, 5, 6, a 3, 5, 6. A 2, 3, 5 is a lower numbering scheme, so I would go down to the chloro. And since I'm going to have a 2-chloro, 3-methyl, 5-nitro, and then a benzoic. Notice the CO2H is automatically number 1 if you use the term benzoic. You could not use ortho, meta, para in this. You would never say ohm, ortho, meta, meta substitution. All right. Now, in terms of physical properties, aromatic hydrocarbons are very nonpolar. They have typical boiling points and melting points of organic compounds. In terms of chemical behavior, many aromatics are carcinogenic. They tend to be the aromatics consisting only of aromatic rings. The carcinogenicity of these molecules is reduced when there are substituents. For example, salicylic acid is a precursor to aspirin. We would not be prescribing a painkiller that was a carcinogen. Acetosalicylic acid is based on this molecule. The reason for the difference in carcinogenicity has to do with the presence of substituents. Oxidation processes on the molecule occur at the substituents, but when there's no substituent, oxidation can yield epoxide-like molecules off aromatic rings. But disrupting the very stable aromatic ring is unfavorable, and such epoxides are extremely reactive and attack DNA. This can lead to cancer and can cause problems. An example of this type of molecule that is extremely carcinogenic is the molecule benzoalpha-pyrene. I expect you to recognize the name. Benzoalpha-pyrene is found in cigarette smoke and automobile exhaust. It is so carcinogenic that just coating a mouse's skin with it causes skin cancer in almost 100% of the cases. So, aromatic rings can be potentially carcinogenic. Well, so far we are familiar with the concept of benzene being resonance stabilized. We're going to talk more about valence bond description, but when we use valence bond theory, we draw resonance structures for benzene. Now, the resonance structure of benzene is the best description we can get using Lewis structures. But the resonance hybrid, some average of these, we draw a circle in the middle of the benzene ring to represent the delocalization of pi electrons over the 6 carbon atoms. Now, what's interesting is we often supply a resonance energy. That is the energy by which the resonance hybrid is more stable than any individual resonance structure. In this case, the resonance energy is observed to be 36.0 kilocalories per mole. Now, how is that energy determined? If the resonance hybrid exists and the individual resonance structure, cyclohexatriene, does not exist, how can you actually calculate an energy? Well, let's consider hydrogenation reactions. For example, if I was to hydrogenate benzene, how much energy is released in producing the molecule cyclohexane? So if this is cyclohexane, how much energy is released when I completely hydrogenate benzene? Now let's be clear about this. Taking benzene, reacting it with 3H2 gas over a platinum catalyst requires extremely harsh conditions. You must use heat and pressure. Remember, the aromatic ring is extremely stable, so hydrogenation is not favored. You often have to go to about 300, 350 degrees Celsius, 300 atmospheres pressure of hydrogen gas to produce cyclohexane. If this reaction is done and the energy released from the reaction measured, you find that benzene can release 49.8 kilocalories per mole. So it's negative because the energy is released. So kilocalories per mole. Well, how does that get us the resonance energy? I mean, after all, the individual resonance structures don't exist. True, but what does exist is the molecule cyclohexene. And when cyclohexene is hydrogenated, H2 gas, platinum, under milder conditions than benzene requires, it will form cyclohexane, and we can measure that heat. The heat liberated is minus 28.6 kilocalories per mole. Now, if one alkene bond requires 28.6 kilocalories per mole, and these cyclohexatrienes in the resonance, individual resonance structures, each one assumes isolated double bonds, no delocalization, then they are like 3 cyclohexenes. Each one's an isolated double bond in a ring. Well, 3 times, and notice I'm not calling it benzene because each individual resonance structure assumes the double bonds are isolated. So it's more like cyclohexa 1, 3, 5 triene. So cyclohexa 1,3,5 triene, if hydrogenated, H2 gas, platinum, generating cyclohexane, would give me just 3 times minus 28.6. And 3 times minus 28.6 is minus 85.8 kilocalories per mole. So if that's the case, this is minus 85.8. Now, if that's minus 85.8, what is this difference in energy? Well, that difference in energy is just the difference between 85.8 and 49.8, or 36.0. Now, clearly, this is an assumption. There's no doubt about that. But recent studies published in the Journal of the American Chemical Society in 2000 have shown heat hydrogenation calculations on a molecule called 4-phenylene. And I'm not going to test you on this, but it's nice to know that there is some experimental evidence out here. What's interesting about this molecule is that the chemical behavior of the central benzene ring acts as if it is isolated double bonds. And so if you hydrogenate it and measure the hydrogenation of that central ring, so you get all the same substituents, but you hydrogenate it so you get a cyclohexane, you should be able to measure the heat of hydrogenation for the cyclohexatriene analog. In this case, the molecule does not delocalize electrons through those pi systems. The problem with this measurement was that cyclohexane is supposed to be in a chair conformer, but because of the ring strain caused by the structure of this molecule, it produces a flat structure, which is strained. The heat energy that was produced by this reaction was minus 71, I believe. See if I can look at minus 71.6 kilocalories per mole. Once they corrected for ring strain, they got a value of minus 83.0 to minus 84.2 kilocalories per mole. Now that is awfully close to the value we had of minus 85.8. And what's really nice about this is one could have argued that taking 3 times the cyclohexene value was just an approximation. It's nice to see that some experiments actually exist out there which confirm or support the proposed heats of hydrogenation for cyclohexatriene. Now, as I stated, this was published by Peter C. Volhart from the University of California, Berkeley, in the Journal American Chemical Society, Volume 122, page 7819, in 2000 AD. Okay. Well, let's discuss the bonding in benzene. Now that we've established that the resonance structure is more stable than cyclohexatriene, chemically, benzene does not react like an alkene. It does not react with KMNO4. It does not react with Br2. And as a result, the chemistry and the heats of hydrogenation all support the concept that this aromaticity, that this benzene ring is more stable than we would expect in a simple cyclohexatriene molecule. Now, the bonding in benzene has its roots historically in the early 1800s. It was known that the molecule was C6H6, but because its reactivity was different, double bonds were not attributed to the molecule. In 1872, Kekulé proposed that benzene contains 3 alternating single and double bonds, but that the double bonds were in rapid equilibrium. So he proposed that our resonance structures, that what we know now as resonance, he proposed that there was an equilibrium between 2 different structures. Now, today, since the 1940s, theories of resonance have developed, and it was confirmed that there is only one structure in solution. And so the equilibrium arrow was replaced with the resonance arrow, and the concept of resonance was presented. Remember, resonance states that neither of these structures actually exist. What exists is a resonance hybrid. Thus was born valence bond theory. The true structure is only a resonance hybrid of these 2 Kekulé resonance structures. In fact, there are more resonance structures, many more you could draw, most of which are minor contributors because of charge separation. For example, I could put a lone pair here, put a minus here, and a plus over here. And separating charge like that will produce countless minor contributors. The 2 major contributors are those that give us the resonance energy. That is, the energy by which they are less stable than the resonance hybrid, which turned out in our case to be 36 kilocalories per mole. To derive the molecular orbitals for these pi bonds, though, we have to go to molecular orbital theory. In molecular orbital theory, each carbon of the benzene ring is known to be bond to 2 carbons and 1 H. Furthermore, each carbon has a 2p orbital, which has 1 electron in it. Now, the 2p orbitals, each lobe has opposite phase. The top lobe I will represent as a plus. This is not charge. This is phase. Bottom lobe is minus. Think of it as where the maximum amplitude in the wave actually occurs. They don't line up. Okay? The wave descriptions for the electrons in each lobe don't align. Now, that means all 6 carbons have these 2 p's. Now, the 6 unhybridized p orbitals are perpendicular to the plane of the ring. Because they're perpendicular to the plane of the ring, we can combine all 6 2p orbitals to generate 6 new molecular orbitals. Because they overlap side to side, they're called pi. If I am to draw a ring at John, and I was to draw the 2p orbitals, how I get 6 different new molecular orbitals from this is by the in-phase and out-of-phase combinations. The lowest energy orbital will be when all the top lobes are of the plus phase and all the bottom lobes are of the minus phase, so you get a total in-phase combination of 6 orbitals. This will generate a benzene ring where you have an orbital with donut shapes above and below this ring from the side-to-side overlap. If you like, this is plus and that's minus. This represents a single orbital that can hold 2 electrons. One low energy orbital. That's pi. What happens next, of course, is that now we start adding some out-of-phase combinations. For example, what if these 3 all had the plus phase orbital up, but these 3 had minus phase up? Well, then you'd get lobes like that, excuse my bad drawings, above and below the plane of the ring, caused by side-to-side overlap, where this is plus minus in phase and that's minus plus. And you get the idea. This would be a single orbital. It could hold 2 electrons. It would be higher energy because of the out-of-phase combination. So as you do this more and more, you get more and more out-of-phase combinations. You go higher and higher in energy, until finally you've completed your pi system, having produced all possible out-of-phase combinations, 6 p orbitals generating 6 pi molecular orbitals, 3 of which are pi, that is bonding, and 3 of which are higher energy pi star. Now, we've got 3 pi's, 3 pi stars. I can put in my electrons. How many electrons do I have to put in? Well, each 2p had 1 electron. 6 are 2p's. I have 6 electrons. 1, 2. Fill lowest energy first, that's Aufbau principle. 3, 4. Degenerate orbitals get 1 electron each of identical spin, that's Huckel Rule. And the Pauli exclusion principle states no more than 2 electrons in an orbital. Notice I get 6 paired up pi electrons, all in bonding levels. The fact that they are paired up makes them especially stable. That they're delocalized over the many atoms gives us a special situation in which there is greater stability. This is what causes aromaticity. So benzene is aromatic because of the ability of side-to-side overlap of these 2 orbitals producing these orbitals that extend over many atoms, delocalizing the electrons over many atoms. Lewis structures, valence bond theory, requires you to draw structures where bonds extend between 2 atoms. You have to go to molecular orbital theory to properly represent orbitals extending over many atoms. Now, I don't expect you to know the shapes of the orbitals for benzene caused by the side-to-side overlap and the in-phase combinations, but what I do require you to know is the energy level pattern, this is increasing energy, that you would get for the pi orbitals. But is this aromaticity restricted only to benzene? For example, consider the molecule cyclohexatriene. In the case of cyclohexatriene, cyclohexatriene, consider, let's write it out, cyclo-octa, or what have we got? 1, 2, 3, 4, 5, 6, 7, 1, 3, 5, 7 tetraene. There we go. Consider this molecule, cycloocta 1357 tetraene. It's similar to benzene. It's a ring structure. It is cyclic. It's sp squared. It has 2 p orbitals that could overlap side to side. Will it produce this aromatic effect, this delocalization of electrons that leads to enhanced stability? Well, in order to answer this question, we need to define, if we can, the requirements for aromaticity. Well, the first requirement is that the molecule must be cyclic and planar. You must have a cyclic planar molecule. After all, if you're going to get 2 p's overlapping side to side in a ring, you must have a ring and it must be flat so all the 2 p's line up. And of course, rule 2 is obvious. If you're going to have side-to-side overlap of 2 p orbitals, you must have p orbitals perpendicular to the plane of the ring. The third condition simply states that you must have a Huckel number of pi electrons. That is the total number of pi electrons when placed equal to the formula 4n plus 2. When you solve for n, if n equals an integer, you're aromatic. If n equals a fraction, you are not aromatic, or what I call anti-aromatic. It's a bit of a misnomer, but If you use it to mean not aromatic, that's fine. So we'll call it anti-aromatic. Now let's apply this to our two molecules that we have drawn. 1,3,5 cyclohexatriene, alias benzene, and 1,3,5,7 cyclooctatetraene. Rule number 1 says the molecules are cyclic. Well, both are cyclic. Rule number 2 says they must get planar. Well, I could imagine, since they're sp squared, that they could go trigonal planar and the whole system could be flat. Rule number 2 states they should have p orbitals perpendicular to the plane of the ring. Since every atom in both structures is sp squared, they will all have 2 p orbitals perpendicular to the plane of the ring. The last one states that pi electrons, when set to equal to 4n plus 2, should yield n equal to an integer. Well, the total number of pi electrons in the cyclohexatriene is 2, 4, 6. 2, 4, 6. We get 6 equals 4n plus 2. 4 equals 4n. 1 equals n. Is 1 an integer? The answer is yes. So benzene, or 1,3,5 cyclohexatriene, is aromatic. And we call it benzene because of that. Cyclooctatetraene, on the other hand, gives us 2, 4, 6, 8. 8 pi electrons. 8 equals 4n plus 2. 6 equals 4n. Or n equals 6/4, which is 3/2, or 1.5, which is a fraction. And hence cyclooctatetraene is anti-aromatic. It is not aromatic. In fact, because it isn't aromatic, the molecule actually adopts a puckered configuration. And we can place pi bonds, thusly. And this is closer to a more accurate representation of the structure actually adopted by the molecule. But one could ask the question, why does the Huckel rule work? Why is it that if 4n plus 2 does not yield an integer, we get an anti-aromatic situation? What actually causes this? In order to understand this, we need some rules that will allow us to set up or generate the energy diagrams so that we can compare the pi molecular orbitals for these two molecules and other molecules. So what we're going to do is give you some molecular orbital energy diagram rules, specifically for pi molecular orbitals, or pi MOs. So pi MO rules, if you like. How can I draw the molecular orbital energy level diagrams for pi systems? Well, I have three main rules that will allow you to draw them. One, you always draw one lowest energy bonding orbital. 2, higher energy orbitals will occur in degenerate pairs. 3, has two parts. At the highest energy orbital, A, for an odd number of p orbitals, so an odd number of p orbitals in the molecule, you will get a pair of degenerate orbitals. And B, for an even number of p orbitals in the molecule, you'll get a single high energy orbital. So let us draw the orbitals for benzene and cyclooctatetraene and compare the occupancy of the electrons in those orbitals. We've already drawn the benzene, but let's follow our rules and see if we can generate the pi system. So here's my benzene molecule. If I count up the pi electrons, I see I have 6. I also have 6 atoms. Each one has a 2p orbital. So when the 2p's overlap side to side, I'm going to generate 6 molecular orbitals. So I know I have to put 6 orbitals in. Rule number 1 stays, start with 1 low energy orbital. So there it is. Now, rule number 2 says you go up in degenerate pairs. Degenerate means equal energy. So here's a pair, equal energy, I'm up to 3 orbitals. Here's another pair, equal energy, I'm up to 5 orbitals. Now my highest energy orbital, I have an even number of p orbitals, so I get a single high energy orbital. I'm going to have 6 p orbitals that mix to make 6 molecular orbitals. I've put in 5, so I'm going to get 1 high energy orbital. Now the top 3 are pi star, the bottom are pi. I can put in my electrons. I've got 6 pi electrons, 1, 2. I follow all 3 rules, the Aufbau principle, Pauli exclusion principle, and Hund's rule. There are my 6 electrons. They're all paired up. And they're in bonding levels, which is a nice plus. Now let's do the same thing, but this time for cyclooctatetraene. So here is, if it was aromatic, it would be flat. So let's draw it flat. Here is cyclooctatetraene. Well, I have to start with 1 low energy orbital. I then go up in degenerate pairs. What's interesting is each carbon has a 2p orbital. In this case, I have 8 2p's. That's going to make 8 molecular orbitals. So I keep going up in degenerate pairs because I want to get 8 orbitals. I'm at 5. Here's 7. Again, I have a total even number per orbital, so that's going to give me 1 high energy. So this would be the aromatic pi system. What's interesting is the halfway point. See, the halfway point between benzene, in benzene case, was this. This is the non-bonding point. Everything above this line is anti-bonding, and everything below this line is bonding. So we had pi's, and everything above it's pi star. Well, clearly this is a pi. This is a pi. This is a pi. Over here we have pi star. Everything up here is pi star. But the halfway point is right here. Those orbitals fall right on the non-bonding line. That's rather. So they'd be non-bonding pi orbitals. Now we can put our electrons in. And we can put in 1. How many electrons do we need? Each pi bond can hold 2. So 2, 4, 6, 8. 1, 2, 3, 4, 5, 6, 7, 8. Look at what's generated. We generate a diradical. It turns out the diradical is unstable. Generating a diradical system is not as stable as keeping isolated double bonds. In the benzene case, all the electrons are paired up. Now this is what is amazing about the 4n plus 2. Whenever you solve 4n plus 2 equal to the pi electrons, if you get n as an integer, you get this pattern. You get all the electrons paired up. But if you try solving it for a system that gives you a fraction, the electrons generate a radical system, which is less stable. And so the formula, the Huckel rule, 4n plus 2 pi electrons, n being an integer, being aromatic, works because all the electrons in the pi system are paired up. We can put that to further test by looking at completely different structures. What structures? For example, we can take a molecule like cyclopentadienyl. This is 1,3-cyclopentadienyl. Now, if I look at 1,3-cyclopentadienyl and I ask, is it aromatic? Your answer should be no, because rule 1 is violated. This carbon right here is sp cubed. Has 2 hydrogens. It's a line formula, so you know there's 2 hydrogens there. It's sp cubed, no 2p orbital. Rules 1 and 2 are violated. It's anti-aromatic. But what happens if I put a positive here? In order to place a positive, I have to remove a hydrogen. That means there's 1 hydrogen when you see a plus off a line formula. Carbocations are sp squared, so there's an empty 2p orbital here. If I do the calculation, 4n plus 2 equals, well, 2 for that pi system, 2 for that pi system, none for the empty 2p orbital. That means I have 4. 4n equals 2. n equals a half. This molecule should be anti-aromatic. Let's apply or generate the pi molecular orbitals for this molecule. Here they are. 1 lowest energy. Now, we have 5 carbons in this ring. There are going to be 5 2p orbitals. I go up in energy in degenerate pairs. I'm now up to 3. Here are 5. I'm done. That's it. 5 2p's give 5 molecular orbitals. Look at what I've generated. The highest energy is a pair. That's because I have an odd number of p orbitals. Now I can put in my 4 electrons. 1, 2, 3, 4. Note, I get unpaired electrons as predicted by the Huckel and giving a fraction. This means this molecule is anti-aromatic. What if I used an anion? Well, if I pulled off H+, I'd only have 1 H off of here. Hybrid orbital numbers, 2 carbons and 1 H is 3. Add 1 for the lone pair, it's sp cubed. sp cubed is low energy state. Remember that lone pairs can rehybridize with the lone pairs in a 2p. So we did this in the inversion of amines in chirality section. So this guy could go sp squared and put the lone pair in a 2p orbital. Ooh. That takes energy. If the molecule were aromatic, it could get that energy from aromaticity. If I do that, I get 2 for the pi electrons, 2 for these pi electrons, and 2 for the 2 electrons in the 2p orbital. 4n plus 2 equals 6. If you solve this, you get n equals 1. Huckel rule states it's aromatic. Is that borne out? Well, I've got the same orbital system for my pi electrons. I put 1, 2, 3, 4, 5, 6. We see that the pi system gives me 6 electrons all paired up, no radicals. Again, the Huckel number giving me an integer gives me all the electrons paired up in the molecular orbitals. Now, it is sufficient just to do the Huckel number calculation if I'm asking you, is this molecule aromatic or anti-aromatic? The top one would be anti-aromatic, the bottom would be aromatic. You only do the orbitals and use them in your explanation if I ask you, show why. Why does the Huckel number work? Why is it that when it's an integer it's aromatic? And so you can show whether you get a radical, diradical, or all the electrons paired up. You need to have one more piece of information, actually two more pieces of information. If you're going to press on and actually use Huckel numbers to identify aromaticity. Clearly you've got to figure out the pi electrons. And you have to know when to count lone pairs. Some molecules have more than one lone pair. This molecule called furan has 2 lone pairs on the oxygen. Now, you should note, though, that if we rehybridize the oxygen to either sp squared or sp, only one orbital, if I try to draw it edge on to show that, only one orbital can hold the lone pair and still give you side-to-side overlap. So here are the two p's that give me that pi bond. Here's the 2 p's that give me the other pi bond. And inside this 2p, I have a lone pair. The second lone pair is in an sp squared. It's perpendicular. Only one of the lone pairs can overlap side to side to delocalize with the pi's. The net result of this is when you have more than one lone pair, okay, and only single bonds, you only can count one lone pair. So, let's write that down. When counting lone pairs, if the atom with more than one lone pair has only single bonds to it, you may count only one of the lone pairs towards the electrons, or towards the pi electron. So in this case, if I was doing 4n plus 2, what would I place it equal to? Well, I have one pi bond to give me 2, another pi bond gives me 2. I can count only one of the lone pairs because he has single bonds to him, 2, 4, 6. 6 electrons. If I solve that, I get n equals to 1, so he is aromatic. What if I have a molecule which has a heteroatom that has a lone pair, but it has a double bond to it? Rule 2, the atom with the lone pair has a multiple bond to it. You cannot count that lone pair. So if I apply rules 1 and 2 to this molecule, because there's a pi bond, I can't count that lone pair. Reason is that lone pair will be in an sp squared orbital just like this one is. The 2p orbital that's available is used in the pi bond. So the lone pair can't be in the 2p orbital that's creating the pi bond. So a lone pair is not perpendicular to the ring. It's in the plane of the ring. It's not available for side-to-side overlap. It can't be counted. Oxygen can only count 1. Again, 2, 4, 6. 4n plus 2 equals 6 electrons. N equals 1. This guy will also be aromatic. Well, there you have it. Utilizing the 3 rules that the molecule must be cyclic and planar, Rule 2 that it must have perpendicular 2p orbitals, and Rule 3 it must have a Huckel number of electrons. Using these rules, you can determine what any kind of ring that you're provided, whether it's aromatic or not. Note, you do not have to derive the orbitals unless asked to. You can actually just do the calculation, count up the electrons. Be sure for heteroatoms that if the oxygen has a single bond, you only count one of the lone pairs, and that if there's a multiple bond, you don't count the lone pairs. Also, watch for questions where you're not given the lone pairs, that perhaps maybe you're just given the molecule furan and the lone pairs aren't shown. In that case, you'll have to calculate the lone pairs using your Lewis structure rules. Okay, well, I think that's enough for this Scribblecast lecture. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening. I hope it's been useful. If you have any questions, don't hesitate to see me at the end of class. Thank you very much.